So, all right, so we begin now. So it's indeed a pleasure to have Vivek, who is going to give the colloquium for today. I supposed to report in my mind on a breakthrough on Hilbert regularity for non-local parabolic p-Laplace type equation. It is a serious non-local extension of the celebrated DiBenedetto theorem. On a personal note, I mean, he's one of the finest analysts that I've interacted with, and it was really a pleasure to have it here. Vivek, you can start.
Thank you. I'm going to talk about the regularity theory for parabolic fractional p-Laplace equations. I'm going to talk about. So I'm going to talk about the Giorgi-Nash-Moser theory for this equation. Maybe there's a problem with this. So I'm going to talk about the Giorgi-Nash-Moser theory for this equation. This is the non-local counterpart of the p-Laplace, the parabolic p-Laplace equation. Giorgi-Nash-Moser theory for the parabolic p-Laplace equation was worked out by DiBenedetto in the mid-80s. So this is a non-local extension of that work. So we will talk about the unique difficulties which come because of the non-locality. So this is a non-local equation, and we prove Holder regularity for this equation, local Holder regularity for this equation for all p and in 1 to infinity, and for all s in 0 to 1. This is based on joint work with Professor Karthik, Adimurthi, and Harsh, who are also in the audience. So to begin with, I'll just talk about what is Giorgi-Nash-Moser theory and where it appears, and why should we study fractional operators, for example. So the result in Giorgi-Nash-Moser theory is to prove Holder regularity for weak solutions to elliptic and parabolic equations which have non-smooth coefficients. So the prototype equation, the one that was worked out by Giorgi-Nash and Moser, is this equation minus divergence A of x grad u, where the matrix A is positive, definite, measurable, and bounded. Positive, definite, uniformly in X. So those are the only requirements that one puts on the matrix A. One does not assume any smoothness assumptions on the matrix A. And for that reason, it is an extremely important theory. And it is one of two non-perturbative theories in the regularity theory of partial differential equations. The other theories are perturbative in the nature, in the sense that they derive their regularity from the regularity of the coefficients. So for example, in Schauder theory, one has the matrix A is in C0 alpha, and then one gets the solution U in C1 alpha. So those are perturbative theory, and this is a non-perturbative theory. So we're talking about local weak solutions of this equation. Local weak solutions have this form, which everyone is familiar with. And the jump from W12, the local solutions are in W12 log. So the jump from W12 log to C0 alpha is a very big one. And in fact, this is the maximal regularity possible for equations that have non-smooth coefficients. So one can construct the matrix A, which are not smooth. So one can construct coefficients A which are not smooth, that is, they're L infinity and they're not continuous, such that they can only have regularity C0 alpha and not more than C0 alpha. Another feature of Giorgi-Nash-Moser theory is that it does not apply to systems of equations. It only applies to scalar equations. And okay, so here is a little motivation one might think of, which is that this is applicable to situations where one has non-smooth coefficients. So for example, there is theory of homogenization where one has coefficients which can have jumps. The coefficients can have jumps. So when one can, for example, construct a material, so the matrix A, it can be defined as a discontinuous matrix which has a jump. So in some part of the domain, so if this is our domain omega, then in some part of the domain we can have the value alpha, and in the complement of that domain we may have the value beta. So this is an example of discontinuous coefficients which come up in applications. For example, in the theory of homogenization, where something like this is very important. To have jumps is important. Similarly, in numerical, so generally speaking, regularity theory is important also in numerical analysis, where the discretization procedures will be based on how much regularity, how much basic regularity the equation that one works with has. So another important feature historically of the Giorgi-Nash-Moser theory is that it offers solutions to Hilbert's 19th problem. So Hilbert's 19th problem is the following. It asks the following question. It asks that if you're looking for the minimizers of a function of this kind, integral f of grad w dx over some domain omega with suitable boundary conditions, then one wants to know whether the minimizer will be smooth or not. So the minimizer w of this functional, whether it will be smooth or not. That was the question which was posed by Hilbert. And this theory also, the Giorgi-Nash-Moser theory also gives a solution to Hilbert's 19th problem. To see that, what one can do is one can look at the Euler-Lagrange equation associated to this minimization problem. This is the Euler-Lagrange equation associated to this minimization problem. And when one wants to know whether the minimizer is smooth or not, what one would want to do is to differentiate the equation. So we differentiate the equation formally, this equation with respect to xk. Once we differentiate this equation with respect to xk, we get another equation of this form. And we can define this wxk to be another function v. Then what we find is that this new function v satisfies an equation of the form which is the main concern of the Giorgi-Nash-Moser theory. So we get an equation of the form minus divergence a of x grad u, which is the equation of concern in the Giorgi-Nash-Moser theory. And these coefficients a of x are defined as the Hessian of the integrand f evaluated at grad w. So this is so in order to solve Hilbert's 19th problem, also one needs to look at an equation of this form. So here what happens is that if somehow we find out that v is C0 alpha, then that implies that W is C1 alpha. So if somehow one finds out that v is so if somehow we find out that v is C0 alpha, so if v is C0 alpha, then W will be C1 alpha, and then the coefficients A will also belong to C0 alpha. So we can check that if the coefficients, sorry, if W is C1 alpha, then grad W is C0 alpha, and then this composition, the Hessian of f composed with grad W, that will be in C0 alpha. And then one can use Schauder theory, and that will give us that v is in C1 alpha. And because v is wxk, therefore we will get that w is C2 alpha. And then once w is C2 alpha, once w is C2 alpha, then the coefficients A will be in C1 alpha. And then one can apply Schauder theory again, and one can bootstrap to get that W will be in, V will be in C2 alpha. And that implies that W will be in C3 alpha. which again implies that A is in C2 alpha. So one can repeat this process again and again repeatedly. And using this bootstrap argument, one can conclude that W is C infinity. So what one wants to do, in fact, is that one should be able to prove that B is in C0 alpha. So we want to prove that B is in C0 alpha. And that is exactly what requires the input of Giorgi-Nash-Moser theory. So that's exactly what's written here, that if W was C1 alpha, then one can bootstrap and get that W is actually C infinity. But to reach W is in C1 alpha, one needs the function B to be in C0 alpha. And that exactly requires Giorgi-Nash-Moser theory, because this is not known. This is not true. So it also gives us a solution to Hilbert's 19th problem. So before I start talking about the Giorgi-Nash-Moser theory, the technical details of the Giorgi-Nash-Moser theory, just a little historical timeline. So the proofs of Holder regularity were worked out by Giorgi-Nash and Moser in these years. And soon after, Ledizhenskaya and Uraltseva, they proved Holder regularity for the p-Laplace equation. And they also proved it for the nonlinear parabolic equation, but with growths of order 2. So Ledizhenskaya and Uraltseva, they also proved Holder regularity for this equation. Where one assumes that A is a nonlinear function, but A has growths of order 2. So, but they were not able to handle the case where this growth condition is replaced with P. So this problem was open for a long time, where the growth condition on the coefficients A is of order P. And this was solved by DiBenedetto in the mid-80s. And this required a new technique. And this technique is known as the method of intrinsic scaling. So for nonlinear equations where you have P growth, this was done by DiBenedetto using a new technique. And this is also something that we use in our proof. Then coming to the non-local operators, for the non-local equation, this is the non-local Laplacian. So this is the fractional Laplacian. So the Giorgi-Nash-Moser theory and other regularity theory for this equation was worked out by a lot of people. A lot of people have worked on it, such as Kasman, Sylvester, Caffarelli, Wasser, Chan, Bass, and there are other names which I'm sure I'm forgetting. But this was worked out by a lot of people. Also, the parabolic counterpart for this equation. So this is the linear equation, and its linear counterpart, the linear parabolic counterpart, was worked out by these people. Then this is the fractional p-Laplace equation. So for the fractional p-Laplace equation, the Giorgi-Nash-Moser theory was worked out by these people, Di Castro, Cusi, and Palatucci, and also by Kozzi, and they used completely different methods. Okay, so now what we have proved is the parabolic version of this equation. The Giorgi-Nash-Moser theory for the parabolic version of this equation. Let me talk about the origins of the fractional operators. Where do they come from? So mathematically, they come in an easy way. So mathematically, we can get the operators using the Euler-Lagrange equation for certain functionals. So as we well know, the Laplacian comes from this functional. If you look at the Euler-Lagrange equation for this functional, then you will get the Laplacian. And everyone knows that if you look at the Euler-Lagrange of this equation, one gets the p-Laplace equation. And so therefore, if you look at the Euler-Lagrange equation for this functional, then you get the fractional p-Laplace equation. And then what we are interested in is the evolution counterpart of this equation. So one can ask, where does this norm come from? So this norm is associated to this functional comes from the WSP norm, and WSP norm we are already familiar with from trace theory, for example. So for the case of this particular functional and the WSP norm, it can come as the trace space for some Sobolev spaces on the upper half plane. So that's the mathematical, that can be a mathematical origin for why one should study a functional of this kind. However, physically, it is a model for nonlinear, non-local diffusion. So everyone knows that the Laplace, or the heat equation rather, the heat equation is a model for diffusion. So the heat equation it's a model for diffusion, which means to spread. So it models the spread of some physical quantities. So for example, in this case, it models the spread of heat. And this is a very special equation in the sense that it models heat in an isotropic and a homogeneous medium. So what that means is that this equation does not care about, in space, it does not care about the direction in which the heat is flowing. All directions are the same for this equation. And homogeneous means that the heat flow does not depend on where we are located in the domain where we are studying this equation. So this is a model for isotropic and non-homogeneous equation. Then the next one to look at is, of course, divergence A of x grad u. So this is a model for anisotropic and heterogeneous diffusion. So this one cares about the direction in which where the heat is flowing, and it also cares about which point we're located at. Then one can look for other kinds of models. So one can look at this model. So this is a non-linear model. So now we have anisotropic heterogeneous heat flow. Now we can add another word to it, which is non-linear. So the reaction of the media reacts to the heat flow in a non-linear way. And then the next one, the equation that we are interested in is this equation. So this is the non-local. So now this equation has 4 properties. It is anisotropic, it is heterogeneous, it is non-linear, and it is non-local. So it is a model for such heat flows. So that's a physical motivation for studying this particular equation. So let me start talking about the technicalities, a little bit about the technicalities. So the main ingredient of the proof of Giorgi-Nash-Moser theory for the equation minus divergence A grad u is this energy estimate. So we consider this energy estimate, which is also called as a Cauchy-Poole inequality, and this energy estimate is worked out for cutoff functions, for functions of this kind, for truncated functions of this kind, u minus k plus and u minus k minus. And this is easy to obtain starting from the equation, and which we're all familiar with. And the proof of Giorgi's theorem is done in 2 steps. So first one proves the boundedness of solutions. So what we know is that the gradient of U is in L2. So the solution U belongs to W12 low. So the gradient is in L2. So using this information that the gradient is in L2, one sets up a certain iteration, sets up a certain iteration using Sobolev embedding to get that U is actually bounded. And in the second step, we prove that assuming that the solution is bounded, one proves that the solution is actually Holder continuous. So the boundedness is proved by a certain iteration that involves the Sobolev embedding. So let's talk about the second part, the second step, which is we want to go from U is in L infinity to U is in C0 alpha. So what one requires is one requires a different formulation of Holder continuity. So we do not use the pointwise formulation of Holder continuity. Instead, we use a different formulation. So the formulation that we use is the following. This definition, which is a pointwise definition, has to be formulated in terms of the oscillation decay. So this is the oscillation decay. What this statement is saying is that one can find a sequence of numbers Rn, which is a sequence of decreasing numbers, decreasing radii. So we want a sequence of concentric balls such that the oscillation of the function on those concentric balls decays in this manner. So the oscillation on the ball of radius Rn will be some omega n, where omega n is also a decreasing sequence. So this 2 here is not really important. This 2 here will change from problem to problem. So this 2 will actually depend on the particular problem that we are considering. So so this is the formulation of Holder continuity that we will use. And this sigma that we see here, so this omega n, it is defined in terms of sigma, and this quantity sigma will depend on alpha, and it will depend on n. So if the function that we are considering, if it is Holder continuous of exponent alpha, then this sigma here will depend on that alpha. And I can work out what that relationship is, but it will take a little while, so let me not go into that. But let us believe that the Holder continuity can be reformulated in this manner in terms of oscillation decay. Now what happens is, so to prove Holder regularity, we will in fact prove this statement. We will prove that the oscillation decays on a sequence of concentric balls. And it turns out that it's actually enough to do it at one stage. So one does not need to prove it at each step. In fact, it is enough to do it at one stage. So one can prove that oscillation on a ball of radius r/2 is less than or equal to some constant sigma times the oscillation on a ball of radius r. So once one gets this statement, if we can prove this statement, then one can prove the remaining steps of the induction. The remaining steps of the induction one can get by rescaling the equation that we're solving. So the equation that we have, which is the following. So the equation that we have is this one. Okay, not that. So this one. So the equation that we have is this one. So it's enough to prove this step, because to get the other steps of the induction, all one needs to do is one needs to rescale this equation at each stage. So I'll probably mention it again in a while. Yeah. So for example, here what we can do first of all is that this r, instead of this r here, we can take r is equal to 1. And that's exactly what I mean by rescaling. So what we can do is, instead of considering u of x, we can define a new function, u tilde of x, as u of rx. Then this function u of rx will satisfy an equation of this kind. So in that sense, it is enough to prove this one step, because when we go to the next step, in the next step we want to prove that the oscillation on b of r by 4 of u is less than or equal to sigma times the oscillation on b of r by 2. So to do this step, what one does is one rescales and then appeals to that statement, and that would be enough. So one rescales in this manner. So for that reason, it is enough to do one step. And not only that, we can also take r is equal to 1, because right. So one can also do one also can assume that r is equal to 1, because if the function u is defined on the domain B of R somewhere, then this new function u tilde, it solves the equation, it solves this equation here. So for this reason, it is enough to take R is equal to 1. So that's one thing. The next thing is that one can also make some other simplifications in this process. One can assume that u is non-negative. One can assume that supremum of u is 1 and the infimum of u is 0. So let me also show how that is done. Sure, yes. So let me quickly just mention how that is done. So we started with the function u, which is in L infinity. So we can start with the assumption that u, so of u is in the ball of radius b1 is some capital M, and the inf of u in b1 is some small m. And then we can define certain new functions. So let us define a new function u1, which is u minus little m divided by capital M minus small m. So if we do this, then for this new function, we will get the property that the supremum of u is 1 and the infimum of u is 0. Similarly, there is another function and for this function also the same properties hold. So in some sense, it is enough to work with these functions, which we will see in the future. So what we want to prove in proving Holder regularities, the so-called expansion of positivity theorem. So the expansion of positivity theorem is the following. It says that if you have some measure type property for the function u, then it can be converted into a pointwise property of this type. So suppose that we start with a measure type property of this type. This property is saying that the function u. So we are dealing with a function which is between 0 and 1. And what this measure type condition is saying is the part of the function which the amount of function which lies above half. So if this is half, then the amount of function which lies above half, it covers half of the chunk of the set. So if this is our ball, B1, then this condition, this measure type condition, is saying that the function, the amount of the function which lies above half, that is a good chunk. It's half of that set, half of that set. So this portion plus this portion, that is half of the ball. So if we have a measure type condition like this, then we can conclude that the function u, we can conclude a pointwise condition for u on half of the set. So on half of the set, we can conclude that u is above a certain number, which might turn out to be this one. So this expansion of positivity theorem converts this measure type information into a pointwise information. And given expansion of positivity theorem, let me prove the oscillation decay for you. So as I mentioned, oscillation decay is what we want to prove. We want to prove this. So given this property, given that this is true, let me prove the expansion of positivity. Let me prove the Holder continuity for you. Let me prove the oscillation decay for you. So we want to prove that the oscillation of u on b of half should be less than or equal to some number times oscillation of u on b of 1. So we start with the oscillation of u on b of half. That is the supremum of u on b of half minus the infimum of u on b of half. Then this theorem tells me some information about the infimum of u on b of half. Now I will use this information here. So I will replace the supremum of u on b half by the supremum of u on b1, which is actually 1. So supremum of u on b1 we said was 1, and the infimum of u is greater than c. So the minus of that is less than minus of c, and we get 1 minus c here. And that's exactly 1 minus c times oscillation of u on b1, because oscillation of u on b1 is 1 minus 0. And this gives us the oscillation decay for the equation. So what I want to say is that in the Giorgi-Nash-Moser theory, the important thing to prove is the expansion of positivity. And that's exactly what we prove even in our case, the non-local parabolic p-Laplace equation. Let me skip the first part. Let me focus on this part. Let me focus on this particular part. What is called as the shrinking lemma. This is what I want to be the focus of this talk. And I just want to indicate how this is done in our case, in the equation that we have worked out. So this is what is called as the shrinking lemma. So what does it say? So we start out with some pointwise information. Yeah, so we started out with some pointwise information like this. So we have the function u, and the measure type information that we have is the following: that the measure of the set where x is u is greater than half is greater than half of the measure of the ball of radius 1. So we started out with some information like this, and using this information, we want to get other kinds of measure informations. So we want to get from this information, we want to get a measure type information of this kind. So we want to get a measure type information at all levels. So this is an information about this is a measure type information for the level half. What we want to get is measure type information at other levels. So what this shrinking lemma tells us is that if you have a measure type information of this type, then you can get measure type information at all levels. At all levels. So this is only information at half. So how does one get information at other levels? So this is a picture of that shrinking lemma. So we want to get an information of this kind. So we want to get that x in V1 such that u is, I think it was 2 delta. So from this information, I want to get an information like this. In pictorial form, it looks like this. So what it is saying is that if I'm given a certain, if I'm given a certain chunk of the set that I want to occupy, then I can tell what level I should be at so that I can get that amount of that chunk of the set. So this is information which is saying that if my function u is above the level half, then that part of the function occupies half of the chunk of the set. So suppose I want to be able to say something about the level of the function such that it occupies a certain chunk. So suppose that I'm given a certain theta in 0, 1. So I want to get, suppose that I want to get information, suppose I want to get the level for which I have a certain chunk of the set. So instead of half here, suppose I want to get 1/4, 1/4 of the chunk of the ball. Then I want to, what should I do with the level? What I need to do is I need to increase the level. Yeah. So yeah. So if I want to get instead of, so suppose that 1 minus eta is 1/4, for example, then I want to find out for what level of u will I get that chunk. So that's what we're doing here. If I want to get 1 minus eta chunk of the ball, then I want to slide this to delta. I want to change this to delta so that I can get that chunk of the ball. And this is done using De-Giorgi isoperimetric inequality. This is what is called as a De-Giorgi isoperimetric inequality. What it does is it looks at the level sets. It looks at the level sets of the function u, and it compares it. So this is a quantitative estimate about the level sets of functions which belong to W1P. So what we can see here is on the left hand side, we have the measure of the set where u is above the level k. We have the measure of the set where u is less than a certain level L. Whereas on the right hand side, we have the measure of the set where u is between L and k. So this is an information which is comparing these three level sets. But the important thing to take away from this inequality is that it actually tells you that W1P functions cannot have jumps. They cannot jump. So for example, you cannot have Heaviside function in W1P spaces. And this is in fact a quantitative form of that fact. Because, for example, if you suppose that the Heaviside function, if it were to be in W1P, then we can look at what happens to all of these level sets. This level set will become 0 because this is the measure of the set between two quantities. So suppose you take L is equal to 0 and you take K is equal to 1, then this will be 0 for the Heaviside function, whereas these will be positive numbers. So this clearly cannot be satisfied for something like the Heaviside function. By Heaviside function, of course, I mean the function u, which is 1 for x positive and 0 for x negative. So let me quickly show you how to get the shrinking lemma. So let me say again. So this is the shrinking lemma, and I want to prove this using De-Giorgi isoperimetric inequality. So we will choose the levels properly. So we will choose k the number k, to be some number of the form 1 upon 2 raised to m, I will take the level L as the number 1 upon 2 raised to m plus 1. And I will write down the Giorgi isoperimetric inequality. So what I have done here is I have just written the Giorgi isoperimetric inequality. This is the term corresponding to k minus L. So we have a k minus L here. This is the term k minus L. This is the measure of the set where u is greater than 1 upon 2 raised to m. And this is the measure of the set where u is less than 1 upon 2 raised to m plus 1. This is the gradient. This is the L2 norm of gradient of u on this particular level. And this is am minus am plus 1, because this part is the measure of the set where u lies between the two levels. So if you look here, there is a part on the right hand side which takes the measure of the set where u lies between the two levels. So this can be written as the measure of the set where u is less than k, and the minus the measure of the set where u is less than L. So what I'm saying is that we can write the measure of the set L less than u less than k as the measure of the set where u is less than k minus the measure of the set where u is less than L. So I can write this in this way. And that's exactly what is written here. Am minus am plus 1, where am is the set where u is less than 1 upon 2 raised to m. Now, in this inequality, I want to estimate all the terms. So I want to estimate this term away. I want to estimate this term away, and I want to keep this term. So we estimate this term first. So to estimate this term, we use the measure type information that we already have. So we have a measure type information of this type. This measure type information we already know. So we use this in the next step. So the set where u is greater than 1 upon 2 raised to m, that set has a measure which is larger than the set of the measure of the set where u is greater than half. And we have some information about the set where u is greater than half. So this part we can estimate from below. So this part we will estimate from below. And this part, the L2 norm of the gradient, this will be estimated using the energy estimate or the Cacciopoli inequality. And this is what we do in the next step. So the L2 norm of the gradient is controlled by u minus k minus squared. So this the L2 norm of the gradient will be controlled by this. So this is exactly the Cacciopoli inequality. And now this function u minus 1 upon 2 raised to m minus, this is actually less than 1 upon 2 raised to m, because u minus 1 upon 2 raised to m minus this function is exactly the maximum of 1 upon 2 raised to m minus u and 0. This is the definition of that function. So I can replace that function with this number. Now I can substitute all of this back into the Giorgi isoperimetric inequality, and I get this inequality, which looks like this. So I have on the right hand side, on the left hand side, I have the measure of the set where u is less than 1 upon 2 raised to m plus 1. Whereas on the right hand side, I have a difference term. The difference term is of the form am minus am plus 1. So I can write that in this manner. So I can write that inequality in this manner. Now this is something on which we can use. So this looks like something where one can get cancellations. So how does one get cancellations here? In order to get cancellations, we add this inequality over a certain range of this little m. So the previous inequality that we have, we add it over a certain range of little m going from 0 to some capital M. And what is important is that it leads to some cancellations on the right hand side. So everything gets cancelled on the right hand side. Only two terms survive, which is A0 and A capital M. And both of them I can again dominate by the measure of the ball. Whereas on the left hand side, I have AM plus 1. What I can do is I can dominate it from below. So I can minorize it from below by taking the smallest of these quantities. The smallest of these quantities is A capital M plus 1. And since there are M plus 1 of those terms, I get this expression on the left-hand side. So if I combine all of these objects together, I get this inequality. A capital M plus 1 is actually the same as the measure of the set where U is less than 1 upon 2 raised to capital M plus 1. And that is less than or equal to some constant upon M plus 1 raised to half, because we had an M plus 1 here.
I think there are at least two in the audience who want to see more. So maybe you can speed up the lecture. So
Sure.
those who do not know it, would not know it anymore.
Right. Okay. Sorry. Yeah. So what I wanted to show
Besides
was,
the three of us.
sorry. So what I wanted to show was that in order to get the shrinking lemma, what we have used is the Giorgi isoparametric inequality. And so I can get this estimate using Giorgi isoparametric inequality. And this is exactly shrinking lemma for a specific choice of capital M. So what I want to show is how does one get this shrinking lemma for our case, in the case of non-local parabolic p-Laplace equation. So the problem here is that there is no Giorgi type isoparametric inequality for functions in the class WSP. Till now, I was talking about this equation. I was talking about the equation minus divergence A of x grad U. The solutions of this equation, they are in W12. W12 is a nice space which has Giorgi isoparametric inequality. This time we are working with the p-Laplace equation, the non-local p-Laplace equation. For the non-local p-Laplace equation, we do not have Giorgi isoparametric inequality. So this is the class of WSP functions. What we have instead is a worse version of Giorgi isoparametric inequality, which is also something that we have proved. So this is a worse version of Giorgi isoparametric inequality. And if you remember, in the Giorgi isoparametric inequality for W1P functions that I showed you earlier, on the right-hand side, we have the measure of the set where U is between L and K. And that exactly corresponds to this term. This ALK is exactly the set where the function is between K and L. So in the isoparametric inequality for W1P functions, we only have this term, but this time we have two terms. We have a term where U lies between L and K, and we have another term where U lies above L. So the problem now is that we do not get the cancellation properties that we got earlier in the local case. So in the local case, we saw that there was a very nice cancellation that was happening because of this, the presence of this term. But now we have this extra term. And because of this extra term, we do not get this cancellation which we wanted. So what is the substitute for this, lack of cancellation in the Giorgi isoparametric inequality? That's what we want to see. So let me skip all of this. There are other issues related to the nonlinearity, and there is an issue related to the tail term. I will not talk about that. Let me just focus on the de-Giorgi isoperimetric inequality. So, of course, this is the main theorem. We prove Holder regularity. And the expansion of positivity theorem looks like this. You have a measure type information on a time slice. So what you start out with is not a measure type information on in the bulk. You start out with a measure type information on a time slice. So here we had information for the ball. We do not have such information here. We have information for a time slice, and that gets converted to a pointwise information on a lot of time slices. So sorry. K rho is in this case it's a cylinder. So mod x minus x naught less than or equal to 2 rho, but this norm is the maximum norm, right? But yeah, of course, this does not matter. This can be a ball. This can be B2 rho. Yeah, these can be B rho here. They don't have to be K2 rho. So the expansion of positivity looks like this.
Intrinsic geometry is seen in how much is spread in the time slice over there.
Yeah. So
it is also present in the field.
Yes. So another feature of this type of Holder regularity is that the cylinders are not straightforward. The cylinders have to be scaled in a certain way. So the cylinders have to be scaled by this factor. The time interval has to be scaled by this factor of L raised to 2 minus P. And the reason for that is that the energy estimate, which comes with an equation of this type, it has some inhomogeneity. So it has a term of order 2, and it also has a term of order P. And one has to homogenize the energy estimate. And in order to homogenize the energy estimate, one needs to scale the time interval using this factor L here. And this is known as the method of intrinsic scaling, which was discovered by DiBenedetto. And then we can see this intrinsic scaling appear everywhere. So what is most important here is that one starts with measure type information on a time slice, and one gets pointwise information on a cylinder. So one gets pointwise information on a cylinder, but the amount of time for which this pointwise information holds depends on the level that you start with. So we started with the level M, and this interval depends on the power, the number M raised to P minus 2. If P is equal to 2, then you will not see this M here, actually. So this is exactly a special feature of the nonlinearity. This is not a feature of non-locality. This is a feature of nonlinearity.
Can you translate this into a intrinsic harmonic estimate if U minus is 0, that is U is globally positive?
I don't think so. There is a problem. Anyway, the tail is defined like this, but what I want to show is the energy estimate. The energy estimate is very different from the standard energy estimate. So in the standard energy estimate, there are two terms, as we remember. Okay, so for this equation, del du minus Laplace u is equal to 0. For this equation, the energy estimate looks like this. You have a sub term of integral over ball w plus squared dx plus there is a gradient term. So here there will be a gradient term mod grad u squared dx dt. So on the left hand side we will have these two terms. On the right hand side I will have just one term, which is u minus k plus squared dx dt. So this is the energy estimate for this equation. So let us look at what are the differences in this case. What are the extra terms? So this is the gradient term. So the gradient term gets replaced with this non-local term here. So this is like a non-local gradient. So this gradient here gets replaced with this non-local term here. Not really the non-local term, it's a fractional gradient term. This term u minus k plus squared is still there. It's here, this one. But you get an extra term. You get also a term of the same kind with exponent p. So this is what I was talking about when I was talking about inhomogeneities in the system. So there is an inhomogeneity in the system. You get two terms of this kind. You get two terms of the LP norm kind. Now there are two additional terms. So this is an additional term, and this is also an additional term. So this term at the end, this is called as a tail term. This is exactly due to the non-locality. So this is because of the part of the function which is far away from the ball. So this needs to be included in the hypothesis. So anything that we want to prove, any local estimate that we want to prove about u, for that we need to make some additional assumptions on the far off term, which is the tail. But now we have an extra term here, which is this one. And as I mentioned earlier, we do not have a de Giorgi isoperimetric inequality in this case. And this term is exactly what we need to use in order to deal with the lack of de Giorgi isoperimetric inequality. And Caffarelli calls it the good term. So, okay, so let me brief, if I have 5 minutes, let me just briefly tell how to get the shrinking lemma from this type of Cacciopoli inequality. So as I mentioned earlier, what one needs to start with a measure type information on a time slice. So we need to start with a measure type information on a time slice. We do not start with information in a cylinder. We start with information on a time slice, and what one does is one propagates this information forward in time. This is not difficult. This is not a difficulty. This is something that we always do for parabolic problems. So you start with some information on a time slice and you propagate that information forward. So that's what I'm indicating in this diagram. And what that looks like is the following. So suppose that you have this information. Suppose you have a measure type information on a time slice, then I can propagate it forward in the following manner. But the theorem, the propagation theorem looks like this. It looks like an alternative. Either this happens or this happens. So what this means is that to prove the propagation information, I need to impose some condition on the tail. The tail needs to be small. So this is what this is saying. If the tail is small in a certain way, then I can propagate the information forward in time. And so what I have written is only for the linear case. In the non-linear case, the time interval will depend on the level m. So in the non-linear case, the time interval will not be 0 to delta rho raised to 2s. It will be of the form 0 to delta m raised to 2 minus p rho raised to sp. So in the non-linear case, the amount of time for which we can propagate the information actually will depend on the level that we started out with, which is m. So I'm just writing this for the linear case. So all I'm saying is that we start with a point with a measure type information on a time slice. I can propagate it forward. This is the statement of shrinking lemma. So the shrinking lemma looks like this. So what are we supposed to do in the shrinking lemma? In the shrinking lemma, you start with some measure type information. and you convert it into a measure type information at other levels for other levels. So that's exactly what we're doing here.
So Vivek, I have a question. So both in the linear as in the nonlinear case, so the tail is like in the case when t equals to 2 is like n plus 2. So that means that it has ordered 2s, right?
Right.
So if I rescale, then I gain this r to the 2s or rho to the 2s outside, right? So even if I don't have that, the tail infinite is the first alternative.
Yes.
If I rescale enough,
No, so the tail is already defined with the rho to the 2s. So
okay.
The r to the sp, it's already there. So so I mean to make it scale invariant, we need to define the tail in this manner. Okay. So so what we want to do is something like this. Right. So so let me show you how this is done very quickly. Let me go back to the energy estimate. This is the energy estimate. Let me just take 2 minutes. So what we have is some measure type information which looks like this. So our measure type information looks like this. So I started with information like this. So I started with u dot comma 0 greater than n intersection b rho is greater than or equal to alpha times b rho. So I started with information on a time slice. This is information on a time slice at time 0. That information got propagated forward in time like this. So this is the propagation of the information. And now I want to use the energy estimate. I want to use a good term to get the shrinking lemma. So I will drop all the other terms on the left hand side. I will only deal with the good term. So the time interval is of this kind. So I will work with cylinders of that kind. So I will it should be 4. So I will deal with cylinders of this kind. Let me write the good term first. So the good term looks like this. And on the right hand side, I have 3 terms. But in the linear case, I will only have 1 term. Sorry. What did you say? Oh yeah. Sorry, where? The card. What happened? X minus y to the power x. Okay. So yeah, sorry. Yes. Yeah. Also, there is a typo there. It's actually mod x naught minus y. So I'm just writing it in the linear case. So this is the good term in the linear case. In the linear case, these 2 terms, the 2 term and the p term, they are the same. So in the linear case, these are the same. Oh, I think I've okay, I've written some things incorrectly. This should be r raised to 2s, and this should be r raised to sp. So what I have on the right hand side is the following: 0 to delta 4 rho raised to 2s d4 rho, and then I have u minus k plus, sorry, u minus k minus. I will be working with u minus k minus instead of u minus k plus. One can write an energy estimate also for u minus k minus. So this is the L2 norm term, and there will be a tail term. So the tail term, from the tail term, I have, so in the tail term it will not be W plus, it will be W minus, because I'm taking the energy estimate with the minuses. So let me write this in a more simple way. Let me just already write this in the following way. Let me write it as tail infinity, whatever that is, multiplied with the L1 norm. So there is an L1 norm here. But now this will be divided by R raised to S. R raised to S. So I'm writing this whole thing like this. Now, U minus K minus is less than or equal to K. This is true. So I will replace all of these with K here. So what do I get? I get, from here I get K squared divided by rho raised to 2s multiplied by the measure of the cylinder. So the measure of the cylinder is, let's call it Q 4 rho. Yeah. Plus, now I have to impose a condition on the tail. I will assume that tail is less than K. So I replace that with K. Again, this is also less than K. So I get a K squared. I should also get a right. This R raised to 2s is actually due to the derivative of the time cutoff, the time cutoff. Yes. 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 Sure. Yeah. And also. Sorry. Okay. So on the right hand side I have something simple. So now I only need to estimate the left hand side. So let me estimate the left hand side. So first thing is that I will estimate this x naught minus y. X naught minus y is less than 4 rho. So therefore 1 upon x naught minus y is greater than 1.4. So that's what I do first. So I'll replace this here. And I'll pull it out. Then I have this information. I want to use this. So I will define K is equal to epsilon m upon 2 raised to j. J in n. Then u is greater than k. The measure of the set. The measure of the set where u is greater than k is the same as the measure of the set where u minus k minus is 0. Right. And this is so k is epsilon m upon 2 raised to j. So I can dominate it by the measure of the set where u is greater than epsilon m. So this is a bigger set than this. So I can replace this part. I can replace this part by the measure type information here. So I will take this entire thing and I will replace the measure type information which is contained here with this. So when I do that, what do I get? I will get. So for this, I'm using this measure type information. I get some constant times the measure of B4 rho divided by 4 rho raised to n plus 2s. This just gets pulled out. Now I have 0 to delta 4 rho raised to 2s integral over p4 rho integral over p4 rho of u minus k minus dy dt, and there is a dx here, and all of this is less than or equal to this here, which is k squared divided by rho raised to 2s. Now this I can replace this with measure type information for u is greater than no, u is less than